Hello, my name is Barcelos, and I'm one of the authors of two online Stein Variational Inference for Control and Dynamics. To operate autonomously, robots need to be able to take complex decisions on varying environments. Oftentimes, these decisions do not have a clear optimal choice, and multiple outcomes have to be taken into account. Historically, MPC is one of the most used methods for control due to its robustness and high sample efficiency. An MPC task can also be formulated as a variational inference problem. In this setting, we are giving a family of policy distributions and a dynamical model. The policies are parameterized by a sequence of actions, and these policies, along with the system dynamics, induce a distribution over future actions and states. Our aim is to minimize the KL divergence between this posterior distribution and the target distribution that minimizes a task-dependent cost functional. In Stein Variational MPC, this minimization is performed through a modified Stein Variational gradient descent algorithm. In SVGD, the posterior distribution at a given time is approximated by a set of particles, and the optimization is carried out by evolving these particles through a sequential flow. In SVMPC, each particle now represents a sequence of actions, and the functional gradient is computed by generating sampled rollouts. The sequential nature of the problem is captured by introducing a shift operator to bootstrap the solution of the subsequent time step given the current posterior distribution. SVMPC assumes that the dynamics model is known and stationary and relies on the closed-loop robustness of the controller to compensate for any localization errors. Moreover, and perhaps more importantly, they consider the future state predictions given by the dynamics model as exact point estimates, which may undermine the performance under more severe model mismatch. In contrast, we propose a new method, Dust MPC, in which the dynamical model incorporates uncertainty through distributions over parameters. This uncertainty, however, needs to be propagated through the optimization procedure and leads to probabilistic outcomes when sampling rollouts. We propose a modified policy update rule, which takes into account both policy and model samples. The resulting risk minimization can be seen as optimizing an ensemble of outcomes per policy. To close the loop, the distribution over the dynamics model parameters is updated at every time step given the real data observed from the system. This posterior update can be performed, for example, using mapping particle filters or sequential SVGD. To demonstrate the importance of considering model uncertainty, we perform a set of simulated and robotic experiments. The first task consisted in navigating a planar maze. The goal is to reach the target on the opposite side while avoiding collisions. Initially, the point mass weight is known, but after 100 steps, the mass increases by 50%. Because Dust MPC considers a distribution over mass and adjusts it with each new observation, it can quickly adapt and avoid collisions, whereas the model mismatch leads SVMPC to crash in several occasions. Here we show the outcome of 10 trials, where collisions are denoted by an X marker. The second task is to perform trajectory tracking on a skid-steering autonomous ground vehicle. As the robot is velocity controlled, the uncertainty parameter in this instance is the inertial center of rotation. Similarly to the previous task, midway through the experiment, we cause a change in the dynamical model by adding extra load to the AGV. This causes SVMPC to lose track of the trajectory and reach an unrecoverable state. We performed the same experiment using Dust MPC. After adjusting to the new inertial center of rotation, the controller is able to keep tracking the desired trajectory. Looking at the plot on the right, again we notice how Dust MPC is able to adjust to the new configuration and maintains a lower tracking error as compared to the baseline. Thank you so much for your attention.